Introduction to Singular Value Decomposition. SVD, or Singular Value Decomposition, is a decomposition that looks like this. So you have any matrix. It doesn't have to be a square matrix. You write it as these two orthogonal matrices. I'm going to explain what orthogonal matrices are later in the video, so don't worry if you don't know what this means. And then you have in the middle the diagonal matrix, and it has the same dimension as the original matrix. What this is saying is that any matrix, it doesn't have to be square, any matrix can be written as some diagonal matrix modified by these two orthogonal matrices. Now this one looks awfully similar to diagonalization of a matrix, where you have A equals to P, some diagonal matrix, and P inverse. And it's even more suspicious because, see, orthogonal matrices are matrices whose transpose is equal to its inverse. So they look very similar. But these two decompositions only coincide if your matrix A is positive, semi-definite, and symmetric in the real case. And in all the other cases, they differ. So don't think of them as same. But they do have some similarities. You have these orthogonal matrices diagonalizing this A. So it's a way to diagonalize a matrix, although these U and V are not the same here. The usual diagonalization, they are the same. Okay. All right. So why do we want to know SVD? Well, that's because it's used for defining pseudo-inverse. It's used to reduce the data in machine learning. It's used for linear regression. It's used for principal component analysis. Recently with the advent of machine learning and data science, this SVD just became a lot more important than in the past. So I'm pretty sure some of you are actually trying to learn this because you need it for your machine learning course or something. Or even if you're just a learner trying to learn this in the context of linear algebra, you'll find that SVD will be one of the most important things that you use from the things you learned in linear algebra. Okay. Now, in this video, I want to explain why such decomposition exists and how you can get such decomposition. And at the end, I'm going to show you a calculation example in Python. Python is a computer language, but don't freak out if you don't know any computer language. Even if you can't do the coding, when you see it, you will see that the calculation does explain how this algorithm gets used. And later on, you might be able to do the Python yourself, so it's not that bad. Okay, so please stick around and watch the last calculation, and it will be really helpful in understanding what I'm trying to explain. Okay. All right. Of course, I will be assuming that you know some stuff, some basic stuff like how to multiply matrices and how to compute eigenvalues and eigenvectors. You need to know some properties of the dot product, and I'm thinking of two properties. Like the first one is if you have u dot v equals to 0, then the two vectors are orthogonal to each other. And also vice versa, if you have two perpendicular vectors u and v, their dot product will be 0. Okay. And another important fact is that for any vector, u dot u is the norm squared. Therefore, if u is a unit vector means its norm is 1, its size 1, length is 1. So in that case, you just have 1 squared, which is 1. So u dot u will be 1 for unit vectors. You also need to know how to compute the normalization of a vector. It's like taking any vector v and you divide it by its size so that it's resized to length 1. This is kind of easy stuff because if you have say a vector of length 3 and you divide this vector by its length, which is 3, then what will be the new vector that you get? It will be size 3. It will be resized to be it will be size 1. It will be resized to 1, right? So that's what this formula is saying, so nothing hard. And then you have to know how to diagonalize an n by n matrix using n linearly independent eigenvectors. Well, this one might be a little more challenging than the others, but I actually have a video for this, and if you watch the video that I made for this, you'll also get to review how to get the eigenvalues and eigenvectors. So if you think you don't know this well enough, then please go and watch that one first before you continue this one, okay? And then lastly, there's the complex conjugate. This is a very easy concept. If you have a plus bi, where I is the square root of -1, if you take the complex conjugate of it, you get a minus bi. And multiplying a plus bi times a minus bi is same as a squared plus b squared. So it's same as the norm squared. So that you have this identity, okay? All right. Now, before I go on, I want to stress again that this video, we are only going to do the case for the real matrices. And I chose this path because it makes things a lot easier to understand. And if you watch this to the end and understand everything, then trying to relearn it in the complex case won't be that hard. And plus, in most cases, you're going to work with real matrices, so the thing that you are going to watch in this video will be most likely what you need. All right, my plan for this lecture is to first explain that dot product between column vectors is U transpose times V. I'm going to explain some properties of symmetric matrices, very important for understanding how we get SVD. I'm going to explain what singular values are, SVD are, and I'm going to explain the algorithm SVD. At this point, it should be clear why this algorithm works, okay? And lastly, I'm going to do the Python example. All right, so now we begin the official part of this lecture. So first I want to talk about transpose. What's a transpose? Well, you have any vector, any matrix, then taking the transpose means you take this blue line, which is a diagonal of the matrix, and you flip the numbers. So 4 goes into 2, 2 goes there, 3 will go over there, so you end up with this matrix. That's called a transpose. So you can see that when you have a transpose, then you have this 1, 2, 3, which is the column. Its transpose becomes a row. So column vectors become row vectors, and vice versa. If you have a row vector, and if you take the transpose, you get the column. Okay, so here's a column that becomes a row. All right, now once you understand what transpose is, then observe that the usual dot product, what's the dot product? It's just the component-wise multiplication you add, right? It's same thing as multiplying these two column vectors. Okay, so a matrix of n by 1 is called a column vector. This is a 3 by 1 column vector. And if you take the transpose, you get a row vector, and if you multiply these two matrices, you end up with a1 times b1, a2 times b2, a3 times b3, which is exactly the formula for the dot product. Okay. Now, dot product, therefore, is U transpose V. Okay, so that's what we're going to use a lot for dot products. And another important property that you have to know about transpose of a matrix is that if you have A times B transpose, that's same as B transpose and A transpose. In other words, their order changes. There's a similar formula for matrices when you take the inverse. If A and B are invertible matrices, then the product is also invertible, so A, B inverse does exist, and this is same as B inverse, A inverse. So their orders change. So something similar to that happens here as well. Now suppose A is an n by n matrix and U and V are n-dimensional column vectors. In other words, n by 1 matrices, I just said that. In that case, you can do the following calculation. You have AU dot it with V, and I explained that, see, A times U, a square matrix times a column vector will again be a column vector. So you're doing a dot product between two column vectors, and we just showed that you calculate the column vector by taking the transpose times the other vector. So rewrite this as the transpose. And then we use this above property. So now these two orders get flipped. So it's UT ATV. And if you look at this like UT times ATV, this is again a square matrix times a column vector. It should give you another square matrix. So you can think of this as U something to transpose times another vector. So that's also the dot product. And if you look at what happened in this calculation, you see that this A now became AT, right? So we say that the AT is the operator adjoint. There's actually a matrix adjoint which has a different meaning. So it's a little confusing, but as an operator, with respect to this dot product, AT is the adjoint, okay? This dot product is also called the inner product. And for the inner product, we have adjoint of a square matrix same as its transpose. Okay. All right, so that was what I wanted to talk about the dot products. Now let's move on to the symmetric matrices, definition and properties. So first, if you have a matrix whose transpose is equal to itself, we call that a symmetric matrix. So as you can see, these are same, these are same, these are same. So if you took this diagonal and you flipped over it, it doesn't change, right? So that's a symmetric matrix. Now, with respect to the dot product U dot V equals UTV, symmetric matrices are self-adjoint because, of course, we just learned that the adjoint of a matrix is its transpose, but it doesn't change. So these matrices have the property that its adjoint is same as itself. Okay. And what it means, even if you didn't understand why this is so important, basically it's saying this: I can move the A to the other one. So if you have two vectors dotted and you have A multiplied only on one side, then you can move it to the other one, and it doesn't. The final outcome is the same. Okay, so that's what self-adjoint means. And strangely, this can be used to prove so many things. Okay. All right. So the first property that I want to talk about is that symmetric matrices have real eigenvalues and real eigenvectors. And when I say symmetric, again, we're talking in the context of real numbers. So if you have a symmetric matrix which has all real elements in it, in that case, all its eigenvalues must be real and all its eigenvectors must be real. It's actually pretty amazing if you consider that there are real matrices whose eigenvalues and eigenvectors are all complex. Okay. All right. So unfortunately, I was saying that we're only going to work with real. To prove that it's real, I have to talk complex. Okay. So we will have to work with this complex version of the inner product. It's called the Hermitian inner product, and the only difference is you take this bar. This is the complex conjugate I talked about, right? So this bar makes I become negative I. So if this is a complex number and its element is like 3 plus I, then its bar would give you 3 minus I. Okay, so that will be done for every element in the vector. You can see that this actually is an extension of the dot product as we know it, because if U and V are both real vectors, then the conjugate doesn't do anything for just purely real numbers. So it's just an extension of the usual inner product that we know. Okay. Now, let's say you have any vector z1, z2, z3. These could be complex numbers. I want to show you something. If you do V inner product with V, then if you do the actual calculation, you end up with Z1 times Z1 bar, Z2 times Z2 bar, and so on and so on. And I said in the beginning that any complex number times its conjugate, it's the norm squared. So these are just squares of each components, absolute value squares of each components. And then that's actually the size of this vector, right? So it is in accordance with what we would imagine if we were to actually define the size of a vector by using this formula v dot v is equal to norm of v squared. Okay, so if this were to hold, even for the complex case, then this bar is necessary so that everything works out correctly. So that's called the Hermitian inner product. Okay, so this is true in general for any vector v, even for like 4-dimensional complex vectors, 5-dimensional complex vectors. This will always be true if we take this Hermitian inner product. Okay, now I want to prove this now. Suppose A is a real symmetric matrix. It's important that it's real. And then you have if V is an eigenvector with eigenvalue lambda, and that this is what it means, right? An eigenvector is where multiplication by a matrix is same as resizing by some constant, and this V has to be a non-zero vector. Okay, so at least one component of this V has to be non-zero, and lambda could be 0, but it's just any number. Okay, right now we don't know if it's complex or real, and we want to prove that lambda has to be real. Okay, all right, so here's what we do. We do the computation. We do AV with V, right? It's this thing, and the transpose switches these two around, and then look at this and say, oh, transpose is same because A is symmetric, right? Moreover, the bar of A is same as A because A is real, so this is same as that. And then once you do this, what we see is that this is really same as V and AV inner product. So we just show that these two are the same. So you can summarize this as a very important property that if you have a real symmetric matrix, then it's self-adjoint even with respect to the Hermitian inner product. Okay? So that's something that's really important. This is the proof. And now you use this fact. What do we get? We get that AV is same as lambda times VT, so lambda can come out, right? And here, again, AV is same as lambda V, but because it's inside this complex conjugate, when you bring it outside, you'll have to say that these two are equal, but this side you have complex conjugate. Now, notice that these are the norms of V as before, right? So if you divide both sides by this, remember, V is a non-zero vector, so its norm cannot be 0. So if you divide, you end up saying lambda satisfies that its complex conjugate is equal to itself. And the only way that this could be true is if the imaginary part is 0, because if it has a non-zero imaginary part, then it will be negated, so these two should be different. Okay, so it looks like a complicated proof, but all you have to remember is that real symmetric matrices are self-adjoint under the Hermitian inner product. In other words, AV V is same as V AV. Okay, so this can move to the other side. All right. Okay. Now that we know lambda is real, to show that it has real eigenvectors, all you have to do is write this down and just take the real part of the vector. It will still satisfy the same thing because A is a real matrix. You can just take the real part of V and multiply it to A. And again, because lambda is real, you can also bring it outside. Okay. If a and lambda were not real, you can't do this, but because these are both real, you can do this. And once you do that, you see that this is, again, some column vector, right? So it satisfies a times something equals lambda times something, with these two being column vectors. So this is indeed the eigenvector. Of course, there could be a problem if the real part is 0, but in that case, we just take the imaginary part both sides. At least one of them has to be non-zero. So taking either one of the two should give you a completely real eigenvector. And that's pretty important for us, okay? All right, now let's go to the second property that we want from the symmetric matrices. The eigenvectors of symmetric matrices with different eigenvalues are orthogonal. Okay, so let's say you have u and v as eigenvectors with eigenvalues a and b. And because it's symmetric, it's real symmetric, we know that a, b, and these vectors are all real. And because a is symmetric, we know that au dot v is u dot av. In other words, these are self-adjoint. You see, adjoints are a very convenient way to prove things, so that's why we like it so much. Okay, so we bring this a to the other side, and then because au is eigenvalue a, and av, v has eigenvalue b because of this, and then we also know that a and b are different, right? If they're different, then this can only hold if these are both 0 or a and b are the same. But a or b are different, so this u dot v has to be 0. But if two vectors dot product with 0, that means they're orthogonal. Okay. And this is actually a pretty cool result because if you have distinct eigenvalues, then all these eigenvectors will be perpendicular to each other, and if you have n of them, then you end up with n linearly independent eigenvectors. Okay, so that brings us to this property 3, which says symmetric matrices can be diagonalized by orthogonal matrices. And to prove this for distinct eigenvalue case is easy. So if your real symmetric matrix has n distinct eigenvalues, then we have n perpendicular or orthogonal eigenvectors. So they form a basis for this space, right? In that case, you can diagonalize this, right? But then, what if, yeah, actually, you can diagonalize it. To give you an idea how to do it is you build this matrix, you construct this matrix P, where this matrix P are made up with these eigenvectors. So V1 is the first eigenvector, V2 is the second eigenvector, and you get Vn as this eigenvector. If you define this as P, then applying P inverse AP will become some diagonal matrix where this diagonal values will be the eigenvalues of this A. Okay, so that actually happens. The problem here is that you can't guarantee that the symmetric matrix you get has n distinct eigenvalues. Some of them might have repeated eigenvalues, right? In that case, this argument cannot be used. So for that case, we need to think about what can be done. But here's something extra that's pretty important. If the eigenvectors are normalized, then matrix P whose columns are the vectors will be orthonormal. Okay, so why is that true? Why is that true? So I said P is made up of V1, V2, and so up till Vn, right? And then if you take the transpose of this, then you have V1, V2, all the way up to Vn. And let's assume that not only we take the eigenvectors, but we normalize all of them. So all of these are unit vectors, size 1 vectors, right? So this is your P transpose. And if you multiply these two, you get this dotted with this, because this is indeed V1 transpose times V1, so it's a dot product. And if you have dot product of V1 by itself, then you get its size, but that's 1, right? So when you do the matrix multiplication of these two, you get 1 in the diagonal, and if you have two distinct ones, V1 dotted with V2, we know that these are all orthogonal to each other, so you're going to get zeros everywhere, and ones only on the diagonal. But what is this? That's the identity matrix, right? So here's a very interesting thing that happens only when you have a symmetric matrix. For a symmetric matrix, if you gather all the eigenvectors and you normalize them, in the case when we have all distinct eigenvalues, then you have this orthogonal matrix. Okay, we call such a matrix orthogonal matrix. So you get another way to say this is that P transpose is same as P inverse, okay? Because they multiply to the identity, that means PT is the P inverse. You can get it by multiplying by P inverse both sides, okay? So there's a very specific type of diagonalization for a real symmetric matrix. It's that you can diagonalize a real symmetric matrix so that the diagonalization looks like some matrix transpose times itself, with the additional condition that this is orthogonal matrix. Okay, so that's what it means to be orthogonal. Okay, so a real matrix that satisfies this is called orthogonal matrix, and what we just saw is that real symmetric matrices can be diagonalized by orthogonal matrices if it has n distinct eigenvalues. Now, so that clears up a lot of things, but as I said, not all symmetric matrices have distinct eigenvalues. So what do we do when we have some symmetric matrices with some of the eigenvalues being equal? Well, in that case, we can only give a heuristic argument, because to actually go through the proof, you need a completely different approach. You probably need 1 semester worth of linear algebra to understand what it means. So I'm just going to give you a heuristic argument. So if you have a symmetric matrix whose eigenvalues, some of the eigenvalues are equal, then you can approximate that matrix by something that has, so let's say you have a matrix whose eigenvalues are like 1, 2, 1, 2, and 2. Then you can approximate this matrix A by some B whose eigenvalues are like 1, 2 plus epsilon, some small value, and 2 minus epsilon. And still maintaining that B is also real symmetric. Now in this case, you have distinct eigenvalues, so this can be diagonalized by the orthogonal matrix P, so that this is a diagonal matrix. And what you do is you can now take a limit where epsilon goes to 0, so that B eventually gets close to A, and that's going to change our P, but still this limit will exist, and some P will be there, so that even for this one you have some P. So think of these as something that depends on epsilon. So you will end up getting some PT of AP as some diagonal matrix. Okay. All right, so that's like the really rough argument. I'm not really sure if it can be actually written as a rigorous proof. But what another thing I want to note is that you know that if matrices are not symmetric, there are matrices which cannot be diagonalized. So you might ask, how is it that you have this argument for symmetric matrices, but you don't have such an argument when it's not symmetric? And the answer is that if you have matrices that satisfy the orthogonal matrices, these matrices are what we call they form something called a compact set. And if you have a limit point in a compact set, it still is inside there, so it's still invertible. But if you just have any matrix, any invertible matrix P, then space of matrices which are invertible is not compact. So if you take the limit of it, you might end up with something that's not compact. So that's like a really mathy way of saying it. If you are like a math major student with maybe 3 years of math courses under your belt, then you'll kind of see what I'm saying. If you didn't get it, it's just math speak. Don't worry about it, okay? But it's just a way to just try to see how this argument can be made sense. Now this is actually a pretty heavy theorem. It's called the spectral theorem for symmetric matrices. And again, I said that if you really want to know the actual proof, the rigorous proof, you need like one semester of linear algebra, something that's proof based. Okay. All right. So we went through all the important properties of the symmetric matrix. And now for the real stuff. Now for the singular value decomposition. First, I have to explain what singular values are. Singular values are the square roots of the eigenvalues of A transpose A. Okay, so for any matrix n by n matrix, you can take A transpose A, and that will be, well, if you take the transpose of this, then see, first you have to flip this around and then take the transpose. So you end up with, oh, I made a mistake here. This should be transpose times this, okay? And oh, no, I did make a mistake. Right. So it's, what you do is you first flip these two around. So it's A, T, and then you take the transpose of each, right? So that's what we get by flipping them. And then A transpose transpose, transpose of transpose would be itself, right? So we get this. And what did we just find? We found out that A transpose A, if you transpose it, you get the same thing. So it's a symmetric matrix. So all its eigenvalues will be real. Now, another thing that you can figure out is that if V is an eigenvector of ATA, I said symmetric matrices will have real eigenvectors with real eigenvalues, right? If I do this dot product, VT, AT, if I do this matrix multiplication, this is really, this is the same thing as AV transpose AV, right? And that's really the dot product between these two, but dot product of a vector by itself is its norm squared, right? So what we just found out is that if we compare this result with this another result where V is the eigenvector of A transpose A, then it's A transpose A times V should be lambda V. And if you bring the lambda outside, and these two should be the same thing because you started with the same thing, then dividing by the norm of V is a non-zero vector, so this is non-zero. So dividing by that, you see that lambda has to be non-negative. It can't be negative, okay? So we get lambda as a non-negative value, so taking the square root is okay, right? So this is well defined, okay? All right, so already from the definition of the symmetric, definition of the singular value requires the understanding of a symmetric matrix. So I hope if you didn't know these properties by now, you're pretty glad that you learned them, okay? If A is a symmetric matrix, then the singular values sigma i's are simply the absolute values of the eigenvalues of A. In other words, symmetric matrices have real eigenvalues, but it can be also plus or minus. In that case, singular values are just the absolute value, okay? And in general, they're different, okay? See, if a matrix is not a square matrix, eigenvalues don't even exist. But even for those, singular values are still defined, okay? One more thing I want to say is that if this symmetric matrix already has all its eigenvalues non-negative, then its singular values and the eigenvalues will be exactly the same, and in that case the usual diagonalization will coincide with singular value decomposition. Okay. Yeah, and also even in the case of square matrices, it's not true that singular values are absolute values of eigenvalues. And here's an example. If you have this matrix, if you take the eigenvalues of this, it's this. So this matrix, because it has 2 on the diagonal, it's upper triangular, and this has 1, you can easily see that 1, 0 multiplied to this is equal to 2, 0, which is 2 times 1, 0. So 1, 0 is a column vector, which is an eigenvector with eigenvalue 2. So eigenvalue of this matrix is 2. But if you actually try to find the singular value is totally unrelated to this one. So you should know that although sometimes eigenvalues are related to the singular values, in most cases there's something different. Okay. All right. Now we can define the SVD, right? And we already went over this, but I just want to say that U and V are orthogonal matrices, which you learned. Okay, so now you know what this definition means. Okay, now this diagonal matrix means that even if it's not a square matrix, you only have some non-zero values in the diagonal, and everything else is 0. Okay, and D has to be same dimension as A. Okay, so probably the most important part of this video lecture, the algorithm for finding SVD. And once you see this algorithm, you'll kind of see why SVD would exist for any matrix. Okay, so what we want to do is, let's start with the assumption that the SVD does exist. So you can write A as 2 orthogonal matrices and D in the middle. Then if you compute A transpose A, then you see that in the middle, see, this transpose switches these around, right? So it's VDU rather than UDV. And in the middle, UTU would be identity because it's orthogonal. Orthogonal matrices have the property that they become identity. So they cancel. Identities, multiplying identity doesn't do anything. So you just have this, right? And then you see that in the middle, you have DTD, and diagonal matrices times the diagonal matrix is, again, diagonal. So that's a diagonal matrix. And on the left side, you have the VT, some matrix times V equal to diagonal. And this is very nice because this is really the diagonalization of this symmetric matrix, right? As I said, ATA is a symmetric matrix, right? So what that tells us is it reveals the identity of V. V is the orthogonal matrix that diagonalizes the real symmetric matrix ATA, and I already explained to you how to find that orthogonal matrix. You just take all the eigenvectors of this and normalize them and put it like V1, V2, and then until Vn with normalized versions, right? And if you call this as V, we used to call it P, but if you call this V, then you would be getting something like this. Just think of this as some diagonal matrix, so it's like orthogonal transpose times the matrix we want times V is some diagonal matrix, okay? All right, so again, we get to use the property of the real symmetric matrix, okay? And the upshot here is that, therefore, if you want to know what V should be, then just figure out what ATA is and diagonalize that. And finding the eigenvectors that diagonalize this will immediately tell you what V would be, Okay. And then recall that the columns of V would be the normalized eigenvectors of ATA, and because the eigenvalues of ATA is what we call this the singular value squared, you end up with this identity. Okay. And yeah, so notice that instead of lambda, I'm writing sigma I squared, because that's the definition. What's the definition of a singular value? It's the square root of the eigenvalue of this matrix, and therefore, if you have the actual eigenvalue, it would be singular value squared. Okay. All right. Then we still have to figure out what u has to be, right? So I'm going to do the following. I'm going to define ui as AVI. Then if you do ui.uj, just use the definition. Ui would be AVI. That's how it's defined. And uj is AVJ. And then if you use a property, we're using this property a lot, that you have to switch this around, right? And because we know that v of j is the eigenvector of this with eigenvalue singular value squared, we get this, which is exactly this. But do you see what's happening here? We're assuming that VI's are the normalized eigenvectors, so this is either 1 or 0. Because if I and j are different, then they're orthogonal. If I and j are equal, then it's v dot v, where v is a unit vector, so it must be 1. Okay? And that's really nice because of that, we know that ui dotted with uj would be 0 if I and j are different. If I and j are different. And ui and ui dotted with will be singular value squared. That's what we just computed. This would be, when this is 1, this will be just singular value squared. And then if we define ui as the normalization of this, right? See, this really means sigma I is same as the norm of ui, right? So what you're doing is you're just making this a unit vector, okay? So if you make the unit vector for ui's as well, then the above is just saying that again the matrix U composed by u1, u2 up till un will be an orthogonal matrix, okay? So we have this, right? And moreover, now if we compute this one, just use the definition, then because we know that this is sigma I squared vi transpose vj, that's what we computed in the previous slide, and therefore sigma I cancels and you end up with this. Okay? And this actually means that since this is non-zero only when I and j are equal, and it's 1 when I and j, it's non-zero when, it's 0 when I and j are different, and it's equal to 1 when I and j are equal. This means it's either sigma I when I and j are equal, and either 0 when I and j are different. So if you actually do this computation, this big matrix, each element of the result will be computed by this, and you end up with a diagonal matrix whose diagonals are the singular values sigma I. Okay? So in summary, here is the algorithm that we found. So first you want to diagonalize ATA, define this matrix U prime as AV, so you just define UI as AVI, right? And then normalize this. Okay? So normalize means you do this, right? and you build this new matrix U, which is made up of these normalized vectors, normalized column vectors. That's going to be your U. And this will make U an orthogonal matrix. And then you compute this, you'll see that it's a diagonal matrix. And therefore, if you have U, T, A, V equals to a diagonal, you can multiply the U and VT both sides. U and VT both sides. And because these are orthogonal matrices, they're inverses of each other. So these just become identity. So you end up with A equals to U dVT, which is exactly the singular value decomposition of A. Okay? So that's it. Hopefully I didn't go too fast. You can always review this video one more time if there's anything that you couldn't understand. And feel free to leave a message if you have any questions looking at this. Now don't go yet. I am going to show you the Python. Okay, so let me show you how to get the singular value decomposition using Python. And I'm going to use a Python version that's available for everyone, so that if you want to follow me, you can follow. This is called Google Colab. It's Google Colab, and you're going to see the first one. And when you click and you click New Notebook, you need a Gmail address, and you have to be logged in order to use it. So click New Notebook, and you're going to be getting something like this. Okay. First, we need to import some libraries, because by default, Python doesn't know how to do these computations. And the library that's most popular and useful for this is NumPy. And we're going to give an alias called np. Enter. And then I'm going to also import some functions in there, which I'm going to be using frequently, which are not there. So I'm going to say from numpy.linearalgebra import eigen h. So this is for Hermitian Hermitian matrices to find the eigenvalues and the eigenvectors. Our case is real symmetric. Real symmetric are always Hermitian. Okay, so this is eigh, and then we have to normalize the vector. So I'm going to get the norm function for finding the norm of a vector. Now you type these, and you have to do Shift Enter for Python to be executed. Now it's executed. And you have to do A equals to, let me use capital A. So capital A is equal to np.array. And arrays are just array of numbers, but as you can see, if you have arrays inside an array, that's like a matrix, because each of these array of numbers are thought as rows of a matrix, and you put commas and then enclose them again by brackets. That gives you a two-dimensional array, which is a matrix. So we're going to define that. And I want to show you how to compute the matrix multiplication. So what you can do is A dot T, that's transpose of A, and then at symbol is matrix multiplication. So if you multiply A transpose by A, then you get this matrix, and as you can see, this is indeed symmetric, right? So these -3, 2 and 2 is 6 and 6, they match. So if you take the transpose of this, it's same as before. Okay. Now for that, I need the eigenvalues and the eigenvectors. So what we want to do is eigh applied to A dot T at A. So because I'm using this, I'm kind of skipping the part where you find the eigenvalues, eigenvectors by hand, and I'm assuming that you know that. Okay, so let's just say that we know how to do that one. Okay, And as you can see, you get these eigenvalues. I made this matrix A so that this will in turn give me some integer eigenvalues. I thought that would be easier to handle. But the same procedure can be used for any matrix of any size. Okay, so just do this, and then you get the eigenvalues. And these arrays, this is like the matrix V, which diagonalizes A dot T multiplied by A. So that's like V. And we can assign the first one as arrays of eigenvalues, and there's a comma, and the second one is V. So the way we can assign them is say EV comma V is equal to this thing. Then if we ask what V is, now V has stored this part, okay? And what's important in this representation is that each of these columns are the eigenvectors for this one, okay? So I told you how V is constructed, right? You first find the eigenvectors, normalize them, and then put them as columns. So these columns are eigenvectors of this thing. And if you do V of 0, it gives you the very first row, which is this top row, right? If you want the first eigenvector, you need colon, comma 0, enter, and you get these values. These values as a row vector, because in Python it's more efficient to write in row vector. So this actually gives you the row vector of the column vector, okay? It's a transpose of the first column vector. Now notice that in Python the indices start from 0. In the slides I had it starting from 1, 2, 3 all the way up till n, right? When in Python it starts from 0. So what I'm going to do now is to define the matrix U, and you do it by saying U0 is A applied to the first column vector of V. And we have to normalize this, right? So we have to divide by its size. So I'm going to take the norm of this thing. Okay, so I'm going to apply that here. And then because this is needed for U0, U1, and U2, I'm going to just copy them. Regular enter just gives you a new line. Change this to 1, 1, 1, 2, 2, 2. Shift enter. Then now I have U0, U1, and U2, and that can be used to define our matrix U, which is again np.array. It's a two-dimensional matrix, two-dimensional array, and so it's array of arrays. These are arrays, so I'm going to say U0, comma U1, comma U2, and the problem with this is, as you see, these are rows, right? So these will be the rows, and that's not what we want. And to turn these rows into columns, we should do the transpose, okay? So there you go. You do this transpose, so these will be taken as column vectors. And once we have the column vectors, great. Now we have the matrix U, and that means if we do U dot T at A, V, then we should be getting a diagonal matrix. And this is actually a diagonal matrix. This E negative 17 means it's very close to 0. It's 10 to the negative 17th power, okay? But if you don't like this, let's round it to, say, 5 decimal places. Okay, so np.round. And I need this to be rounded to decimals equals to 5. And there you have it, right? So we see that what this thing says is that A is equal to, if you multiply the U to the other side and V transpose to the other side, and then you can see that A is this, if we call that D, this is the same thing as U at D at V transpose, which is exactly is the singular value decomposition, right? So we're done, okay? Oh, I should show you what U looks like. So U looks like this. So what we just have proved is that if you have this U dotted, you do the matrix multiplication with this D and with this V, then it will be same as A. So we've succeeded in getting the singular value decomposition of A.